Jordan Last from Dimension Labs again. Today we will be discussing cross-canister calls. We'll be discussing, I guess, cycles and performance a little bit, timers, and yeah, basically all that. So let's dive in. Okay, so the relevant chapters today in the ASIL book. First would be chapter 13. This goes into everything cross-canister. Next would be in the reference section, chapter 20.4.8, the instruction counter. Also in the reference section, 20.4.10, performance counter. These are basically the same API, but there's a slight difference. And then in the reference section, chapter 20.10, timers, or chapter 17, timers. So that's what we're going over. And then this documentation from the internetcomputer.org website, gas and cycles cost. So we will start with cross-canister calls. As always, remember, there are tons of examples that you can find in the repository if you need to check the syntax and see what's going on. So just to show you again, you can obviously click the links, but they're all here in the main Dimension Labs ASIL repo under the examples directory. Okay, so here's the main concept. A canister is a single instance of an application on the internet computer, right? It has your code, it has the state, the heap, the stable memory, all that stuff. But there's just one of them. Like one canister is one instance of all that. And as we discussed, there are limitations on that canister, right? You only have up to 4 gigabytes of heap. You only have up to 64 gigabytes of stable memory. Also, you're going to be limited by how many requests, like query calls and update calls, you can handle per unit of time per canister. If I remember correctly, I don't know, maybe I shouldn't throw numbers out there, but you'll be doing maybe tens of thousands of queries per second max, and maybe 1,000 updates per second max per canister, or maybe per subnet. So yeah, the point is that you have limitations. So, and also your canister isn't the only thing that's important. All the applications on the internet computer are their own canisters or sets of canisters. So it's very important to be able to communicate between canisters, either to scale your own application by having a multi-canister architecture. For example, imagine a database that is sharded over multiple canisters. You would need to read and write between them. Or just imagine you're a canister that's doing a token transfer or any other kind of functionality. You're going to need to talk to these other canisters. Also, things like HTTP requests and a lot of other functionality are done through cross-canister calls to the virtual management canister. So cross-canister calls are very, very important. An analogy to Ethereum, if you are familiar with Ethereum, would be calling another smart contract, right? Very important. So let's start with the simplest types of cross-canister calls, and that would be something on the management canister. So we're going to import the management canister from ASIL/canister/management. Okay, this is an instance of the management canister already created for you. And what we're going to do first is we're just going to get some randomness. So we're going to make an update function. We're going to import the blob type, and we'll probably need the match function. Okay, so I'm just going to make a normal update function called get randomness. But because it's a cross-canister call, it's actually going to be asynchronous. So I'm going to tack on the async keyword. I'm going to say that it returns a promise that will return a blob. Okay. So what I'm going to do is I'm going to await a call to the management canister's raw rand function. I'm going to actually execute it like that. So let me back up. The management canister has many methods that you can call, right? There's Bitcoin functionality. There's status of the canister, creating, deleting, depositing cycles, installing code, all kinds of stuff, signing with UCDSA, starting, stopping, all kinds of things like that. One of those methods is called raw rand. This will actually hook into the verifiable randomness that the internet computer provides, and you'll be able to pull in some random bytes, and you can use those random bytes to seed random number generators and whatever you might need randomness for. It's just a very low level way of doing it. And then you need to tack on this dot call to actually get the thing to execute. Once you do that, this will be asynchronous, right? So while this is off doing its asynchronous stuff, your canister is still going to be able to process other update calls. And it can always process query calls. Query calls are running concurrently and possibly in parallel. Maybe in the future they'll be in parallel, but definitely concurrently. And then update calls using these async await, at least under the hood, using their asynchronicity, they're able to handle concurrency at the update level, which is very nice. Otherwise, my understanding is your canister would freeze, and all other update calls coming in would have to wait for this raw rand call to finish, which is not necessarily good for scalability. Once you have a result, keep in mind that it is something we call a call result. So if you look at raw rand, it returns a call result with the blob inside of it, the uint data array. This call, generally speaking, is not going to throw, right? There could be weird bugs or something that would cause it to throw. But if everything is programmed correctly in ASL, and there aren't, I don't know, crazy nuanced issues, the internet computer is going to guarantee that this call returns. It will either return your result or it will return an error. So you have the guarantee. So this is a result with an OK and an error property. Don't try to catch this. Right? You might be tempted to do this. Well, that doesn't do anything. It literally will do nothing for you, basically. What you need to do is treat this as any other result or any other variant, like we've talked about in other lectures. So one easy way to do this is to use the match function. So I'm going to match on the result. That's going to force me to handle each case. So if it's OK, then I'll have my randomness. And I can just return the randomness. If there's an error, we could just return an empty array, or we could trap. Nothing for IC. And you determine what you want to do. You probably want to return a result here, right? And you can say result string. But let's just keep it simple for the moment. Let's just return an empty array if there is no. And then you don't need this parameter. Okay, so we've handled every case that is possible from result. And in the best case, we're actually going to get our randomness. So let's deploy that. Actually, right. We have multiple canisters today, so let's just deploy hello world so we don't have to wait. Okay, so hopefully that was all clear. The management canister is a virtual canister. It's not truly necessarily a canister like your application running, but it does have the same interface as a canister, and you're going to interact with it just like you would other canisters. And yeah, this is like the simplest cross-canister call you can do. I like to use it to test things out. Okay, we're going to call our hello world canister, and we're going to get some randomness. If all goes well, it's going to return a blob with a bunch of bytes in it. Yeah. And every time we call it, you'll notice these bytes are different. Pretty cool. A note on randomness, ASL does seed randomness under the hood for you. So if you use something like math .random. This will also be random. So just an FYI. Cool. That is the simplest cross-canister call to a canister that already exists. But what if you want to talk to your own canisters or other people's canisters? Well, in that case, you're going to have to deal with creating something called a service. So we've got 3 canisters here. One is hello world. That's just where we're going to do some general purpose stuff. And then we have canister 1 and canister 2. Canister 1 is in canister1.ts with canister1.did. And canister 2 is in canister2.ts with canister2.did. So we're going to play around with this. We're going to have one of the canisters talk to the other canister. Okay. So we're going to have canister 1 call into canister 2. So we'll start with canister 2. In canister 2, we're just going to make it a normal canister with normal update or query methods. So we'll just start with an update method. Let's just call it log, and we'll log some message that's passed in. And we'll just print that message. And we can print it too, so we can see. Prove that this is working. Okay. So very simple. One update method, log. It will just print the message and return the message as well. So let's go to canister 1. Canister 1, we want it to do a cross-canister call into canister 2. So we need to create a service definition or a service class. And service is analogous to canister. They're going to be called services though. So we're going to import a couple things. We're going to import the service superclass. We're going to import the service update decorator. We're going to import call result. And we need to import update as well. All those from Hazel. We're going to just say call canister 2 log. We also need to import principal because we need the canister 2 ID. And this will return, it needs to be asynchronous, and we will return the string. Thanks. Okay. So what we're going to do, we'll fill out that body in a second. Now let's define the service of canister 2. Make a class called canister 2. We're going to extend service. And now we need to define each of the methods on canister 2. So we have one update method called log, which takes a string and returns a string. So we mark it as an update, put the name in, put the parameter, and we put the return type, which you must wrap in call result. Okay, that is a very, very simple service definition for canister 2. Now down here, if we want to instantiate canister 2, make a variable called canister 2, it will be an instance of canister 2, and we'll pass in the canister 2 ID. Okay, now this is a canister 2, and you can call things on it. So let's get our result back. Notice I've got, I can grab the ID back if I wanted it, but I have my log function. And we need to pass in some kind of message, so maybe we could pass the message in from here. And we will call it. Sweet. And of course, it is a result. So let's match our result. Handle both cases. In this case, I'll just, a nice way to make sure this looks nice is just to stringify the error. Okay, so I'll let you stare at this just for a second. Sorry, let me deploy it, and then we'll basically we can just deploy everything at this point. All right, so we've defined canister 2. This is the main concept here is you need to have your TypeScript definition of the canister that you're calling, basically. So this one we did by hand. In our other example, the management canister, this was already done for us. So if you go look, there's a class called management. And the ASA project, all we did was we made the service for you. And I expect this is how a lot of services will be created in the future, right? Like if you create an application and you want other people to be able to interact with it easily, you will create this service, and you will, in your npm package that you put, deploy to npm or whatever, you'll let people import that from you. Or in the future, what we might do is we might make tooling that can read a candid file and can generate the service from the candid file as well. Okay, these should be just about done. Awesome. So we need to grab our canister2 ID to pass into canister1. Let's go back here, canister1. We're going to just call canister2 log. We'll pass in canister2's ID. We'll pass in a message. It will instantiate an instance of canister2. Remember, this could be any ID, right? This is just a general purpose definition and interface. And you could push as many of these canisters as you want out to mainnet. And so you would need to know which one you're talking to, and that's what the ID is for. And then we will call the log method on canister2 and pass the message in. It will print the message and return the message. We'll get the result back, we'll match. If it's okay, we'll just return the message. And if it's not okay, we will print there. So there we go. Right, canister, call canister2 log. There we go. Pass in the principal and pass in a message. This is the message. Here we go. Oh dear. Let's take a look. Call canister2 log. Let's check the did files. Oh wait, I just called the wrong canister. Canister1. There we go. Okay, we got this as the message back, and then in the terminal, terminal with replica, notice that it printed this is the message. So we went from canister1 to canister2, canister2 printed it, returned it all the way back. Cool. Notice these were all update calls. This is an update call. This is an update call. So notice, it's taking a little bit, right? If these canisters are on the same subnet, then if you're within under the hood, like the same block, these calls can be quite fast. Within the same subnet, generally you want to make sure to deploy your canister to the same subnet. If your canisters are across subnets, then that latency of the cross canister call I think could be quite high. I think like 5 to 10 seconds. So just an FYI on that. Now these are update calls though. So wouldn't it be nice if, for example, this is just logging. Wouldn't it be cool if it were also, if you could just query it, right? And then it could just be super fast. Well, you can do that, and it's called composite queries. And in ASL, a composite query is it's the same as an update. It's just an async query. So let's do an end-to-end query. Let's start in canister2. Let's pretend we're reading some database string or something, right? It does need to be async. Oh no, this doesn't need to be async. This is just normal query. Okay. So yeah, this method represents wanting to read something very quickly from a database, and it will return a string. So we just need to go add this to our definition here. In this case, though, it's a service query. Has no parameter, but it will return a call result with the string inside. Very nice. Then over here, I will make a query method call canaster2 read string, and this should return. Yeah, we got to do everything we did here basically. This. There we go. This is a query, so it should be really fast. So let's redeploy. Let's go over what we did. We added to our canaster2 service definition a query method. Everything is the same when you define it. If you just mark it as query. We marked this as query. Remember, none of this is going to go through consensus, so therefore it's going to be super fast. And also keep in mind, I don't know if we talked about this, but because it doesn't go through consensus, it has different security properties, right? So you might not be able to trust these results as much as you would trust an update call because they're going to come back from one node. There are ways to mitigate that are currently live and possibly some other things that are coming in the future. The semantics, at least the syntax here is exactly the same. And we'll match. And over here, look, it's just a normal query, nothing crazy. Okay, here we go. Next canister call, we're going to call canister1. Call canister2, read db, and pass in canister2's. Wow, see, that was like super fast. Okay, so there are some rules about composite queries. If you go into chapter 12, cross canister, we do talk about that. Let me just go over those rules with you real quick. So here we are. So far, we have only shown, this is just talking about in this chapter, a cross canister call from an update method. Update methods can call other update methods or query methods, but not composite query methods, as discussed below. If an update method calls a query method, that query method will be called in replicated mode. Replicated mode engages the consensus process, but for queries, the state will still be discarded. So just real quick, if I mark this as an update, according to those rules, this will still work calling a query, but it will be slow because it will call this query in something called replicated mode, where it will still do some kind of consensus, but it will not keep the state. Cross-canister calls can also be initiated from query methods, and that's what we were showing. These are known as composite queries, and in ASIL, they're simply async query methods. And here's the rule. Composite queries can call other composite query methods and regular query methods. Composite queries cannot call update methods. So yeah, just basically update methods can call update methods and query methods, but it's all going to be slow. Query methods cannot call update methods. And it'll be super fast. There you go. I think that's the basic idea. So yeah, I mean, that's a very good overview of defining services, doing cross-canister calls. Something we should also go over would be how to add cycles to these calls. So on the internet computer, so yeah, let's talk about cycles, and then I'll show you in cross-canister calls how you add cycles if you need to. So yeah, I recommend going to the official documentation to get a deeper dive on cycles. But basically, everything, I mean, not everything, but the idea is to meter all costs on the internet computer and charge those costs to the developer, to the user, using something called a cycle. A cycle is basically a unit of computation or a unit of storage or a unit of network resources, like bandwidth, bytes coming over over the internet. And you get cycles by converting ICP into cycles. Basically, their protocol or the system canister provides you the ability to take ICP and turn it into cycles. And canisters have balances of cycles. And the internet computer is keeping track of operations that are happening and storage and lengths of time, and it's constantly depleting the cycle balance in your canister according to everything that's happening. Something very interesting is that right now, query calls, there are no cycle costs for query calls whatsoever. That will probably be changing in the future. They are preparing and doing analysis right now to understand query calls and how much that's going to cost people. But the idea is that, I mean, if you think in the long run and if you think about a cloud platform, we need to charge, like the system needs to charge for the actual cost and needs to compensate the node operators, right? Because otherwise the node operators will go out of business because they will be paying more than they're receiving. So it's important that this is all very accurate. But right now, your update methods are the ones to really worry about, and cross-canister calls and things like that. A good question is if composite queries cost cycles, because those do cross-canister stuff. So I don't know about that. There's all these really nuanced rules, so you'd have to go take a look. But hopefully that makes sense. The basic idea, it's like Ethereum gas, right? Basically everything is going to cost something. And in here, you can go and you can look at the cycle costs for different operations. For example, every time a canister is created, and you can see based on how many nodes are in your subnet, how the costs scale. So a smaller subnet with less replication will be less expensive, and a bigger subnet with more replication will be more expensive. So for example, creating a canister on a normal application subnet, 100 billion cycles. Keep in mind that 1 trillion cycles is about $1.30, $1.40. 1 trillion cycles is set to match the price of one XDR or SDR. It's an asset called a special drawing right, and it's basically trying to be a basket of fiat currencies that is supposed to be stable, I suppose. So that's what that's doing. So usually in my mind, just to keep it simple, I just think 1 trillion cycles is $1, and that gives you like a rough estimate, a US dollar. Yeah, so notice things like compute percent allocated per second. So every second, and for every percentage of computation that you've allocated, then it's going to be costing 10 million cycles. Every update message is just going to cost 590,000 cycles. Every 10 update instructions, 4 cycles. So you can see cross-canister calls. Every cross-canister call has a base price of 260,000. And yeah, so yeah, take a look at all this information. I think that's, yeah, there you go. Tons of information here. So some of this, it should give you a rough idea of what's going on, but I mean, for example, the 10 update instructions per second, well, you would need to know how many update instructions your update method is executing. So how would you do that? That's where the performance counter and the instruction counter come in. So let's just talk about the performance counter and get that out of the way. The performance counter is just a general purpose performance API. You can pass in a parameter here that tells you under the hood which performance metric you want to look at. The instruction counter is is performance counter 0. So the instruction counter returns the number of instructions that the canister executed since the last entry point. And an entry point basically being, the start of an update call in all of its various forms, which would be, if you have a timer, that's going to start an update call when that callback gets executed. If you do a cross canister call, that callback when the call returns is going to be another entry point, I believe. So that's basically what that means. And using the instruction counter, you can actually count the number of instructions. So let's do a little example of that. Yeah, let's count well, no, this one's a little complicated because we do have async await. So we'd have to count the instructions before the async await, because this is one entry point, and then we have to count them after, because after an await point, that's another entry point for the system. So to keep it simple, let's just do a query call. Okay. People asked, I think, to not overwrite things. So count instructions. And in this case, we're going to return a NAT64, which is what the instruction counter returns, I believe. Still need IC. NAT64. Okay, this is like the most basic defects deploy. Let's get the hello world deployed. This will just tell you more or less the base cost of running this query on Hazel. Right? There's nothing really happening except all the under the hood stuff that is necessary to get this call going. All the candidate serialization and deserialization, I believe, will be in here, and the JavaScript VM being spun up and executed and all that. Okay, so let's just count those instructions. Defects canister call hello world. 264,661 instructions as a base cost here, right? So out of a trillion, that's just not very much, right? I mean, it'd be a very, very small amount of actual money if you tried to convert that into the actual cycle cost. How would you convert this to cycle cost, though? Well, technically it's a query, so there are no cycle costs, but if it was an update, then you would take 264,661 and you go to the table. It says 10 update instructions, right? 10 update instructions costs 4 cycles on a 13-node subnet. So you would divide this by 10, I believe, right? So 26,000, more or less. And then you'd multiply 26,000 by 4, and that would get you the number of cycles. And then you just think, oh, well, if it's this many cycles and a trillion cycles is $1, then you can get the actual cost of running that. So hopefully that was helpful, and hopefully you can see what you need to do to use it. Let's try to do this. So we'll do the instructions before and we'll do the instructions after. Though I'm just trying to think if all of this, I don't know. It might be a little too complicated to do right now. I just don't know the exact semantics of when this would work. But so it is a little bit annoying to deal with the instruction counter because you have to go into your source code and actually change things, right? As we're seeing right now. So I've been pushing a lot to get some better performance tools so that you don't have to rewrite anything. And there are some other tools out there. There's flame graphs that I know you can at least use for Motoko, and I'm not sure if you can use them for Rust, but assuming you can, then you should be able to use them for Hazel canisters as well. There are a few other tools out there to do performance stuff. All the benchmarking we've done, though, was basically using the performance counter, which is basically the instruction counter. So we have not done a bunch of benchmarks since then, so we're not up to date on the absolute latest tools. But as I said in other lectures, we are working on swapping out the underlying JavaScript engine to a much better engine that should be much faster. So at that point, we will probably dig into all the benchmarking again, and we should be able to provide some nice details about how performance has improved and maybe show you examples of how you would do this type of benchmarking using the latest stuff. So hopefully that's somewhat helpful. And then I guess the final thing to cover today would be timers. Timers are really cool. So let's talk about the story of timers on the internet computer. This is completely unrelated to that, so let's just start over. So let's say you want to do some kind of cron job or operation on the internet computer where at some point in the future you want to execute something automatically without you having to call something. Because if you have to call something, then you would need some kind of infrastructure outside of the internet computer to do it. Well, the original way to do this on the internet computer is with something called a heartbeat. And a heartbeat runs basically every second. So it's a very crude, very simple mechanism for doing cron job type stuff, because every second you could check what time it is and keep track of that and then decide when to do something. So this is the crudest, simplest, most expensive way, because it's going to be doing basically an update call every second to do some kind of a cron job. So basically, I don't recommend doing this. So I'll deploy this, and you'll see in the replica terminal, it's just going to be logging heartbeat called all the time. Yeah, there we go. Heartbeat called, heartbeat called, heartbeat called. So yeah, super rudimentary, not what you want. Well, because of all the problems with heartbeat, we got a new API, the timer API, which is way better. I'm going to delete the heartbeat because I don't want it messing with what we're doing. I can just comment it out. So instead of just running every second, imagine if you could choose a time in the future to run or choose an interval to run on. Well, that's what the timers do. So let's make an update function. Call it set timer. We'll also import a type called duration. It's just a NAT64 under the hood. And we'll pass in a duration. And let's register a timer. What do you do? It's very much like the set timeout API in JavaScript. Let's see, timer called. At duration seconds. Cool. Let's deploy. So you should see that the heartbeat will be wiped because we're deploying. Yeah, you should see this heartbeat stop very soon. And I think it has stopped. Okay, and then we'll call set timer. And I don't know, 5 seconds in the future. Okay, let's wait for it. Aha, timer called at 5 seconds. Then if you want to do some kind of interval, an interval is also a duration. It's very simple. So timer interval. And we would say interval called every time we deploy, by the way, any timer or any interval that you set is going to be wiped. FYI. What these return, though, is something called, if you go look here, it returns a timer ID. And with timer IDs, you are able to clear the timers. I'll just show you that here. So if you do want to ever have the ability to clear one without deploying, then you can save these timer IDs somewhere, and then you can clear them manually. Okay, so now I should be able to call the timer interval and maybe do every 3 seconds. Interval called every 3 seconds. Every 3 seconds. Okay. So yeah, those are timers. I feel like I'm ready for questions.
Yep, there are quite a few questions, so I didn't interrupt you, but yeah, we had a lot. So maybe I can take it from the beginning. So the first question was, what is IC.trap?
Yeah, IC.trap will end. So on the internet computer or in WASM more. So the internet computer is a WASM environment, right? At the core, these are WebAssembly instructions that are executing on the internet computer. Everything's compiled down basically to run in WASM. In WASM, a trap, I believe it's a WASM concept, a trap will end execution. It's like throwing an error. So if you trap, you just end execution, and everything for that update call or that entry point, all that state will be wiped. So that's what a trap is. You could also throw an error, it will also trap.
Yeah. Uh, how do we make sure that our canisters are in the same subnet?
There's no really nice way to do that. Um, there are some hacks people have come up with. I'm trying to remember how they did it. Yeah, right now there's no official way that I know of to deploy to a specific subnet. But I think what happens is if you use the same, I think what happens is that your cycle wallet, every canister that you deploy from that cycle wallet will be on the same subnet. So I think by default, as long as you're not changing cycle wallets between deploys, they will be on the same subnet.
Yeah, I also think the same. And I also know for sure that if you deploy a canister from another canister, it will be in the same subnet.
Yeah,
So you
and that's how
can
that's
programmatically
how deployment
deploy.
works.
Yeah.
Yep.
Okay, related question. How do we know which canister which subnet is the canister living in?
You could look up the canister ID on like one of these dashboard things, and I assume it would tell you the subnet ID. I don't know where they get this information. I don't think there's an easy way to do it, unfortunately. So every subnet has like a range of canister IDs that it owns, basically. So technically speaking, you should be able to somehow query all the ranges from all the subnets, and then you would take your canister ID and you should see which you would be able to tell which subnet you're in by comparing it against those ranges. But there's no nice way to do that, as far as I know.
Uh, I agree. I also think it's there is no direct way to know. So what extensions are you using for your environment for ASO for your idea?
There are no extensions that I know of that are specific to ASL. It's just VS Code.
Yeah, I think maybe if the person if Mark you want to precise, maybe you saw some extension. Uh,
Yeah, VS
so the
Code has
calls,
really good TypeScript support. So we are not using, as far as I know, nothing specific to ASL.
mm, what is the Sorry. So there was a question asking if the calls from the front-end canister to the back-end canister is a special cross-canister call.
No, a front-end canisters, the canister doesn't talk to anything. The front-end canister just has your static assets. It just has your JavaScript, CSS, and HTML. And the web browser does an HTTP request into the canister and pulls those assets into the browser. Once it's running on the browser, it's not a canister anymore. It's just running in the browser. So any requests you're doing to canisters are just normal HTTP requests. There's nothing cross-canister call about that. It's just a normal ingress message on the internet computer.
Mm, so there is a question, I think a bit off topic, but yeah, if I want to reuse a canister, how do I install the code to that specific canister ID? Yeah.
Uh, you just deploy to that canister ID. So, um, for example, let's say I don't want hello world to be hello world anymore. Then I could just change the path to the TypeScript in the candid, or I could change the path to the wasm binary, and then DFX will redeploy over and should use the same canister ID. So yeah, that's how you
Yeah.
can do it in DFX. You just deploy over it. Just use the same canister ID and deploy a new app to it.
What exactly is randomness? So I think you use randomness in the demonstration at some point. What is it exactly in terms of variable? Yeah.
Uh, it's random bytes. That's the basic concept. It's random bytes. So whatever you need random bytes for, if you need to make, it's a very low level thing. So if you need to make a random number generator on your own or seed randomness on your own or something, then you can grab randomness from the internet computer. It's a core primitive that the internet computer gives you. So, for example, the Node.js crypto API or the web crypto API, those APIs ask for randomness. So if we want to provide those APIs to you, we would have to use the randomness of the internet computer to seed those APIs so that they're secure. So, I mean, it's just raw randomness, which is useful for anything that requires randomness, basically.
Mm, so the next question is, can we simultaneously call an update call on the main canister and then a cross canister call? If yes, one of those calls will be discarded, right? I'm not 100% sure of the question. So if you want to
Yeah, can
write it
I read
again,
that question? Is it in the
yeah,
Q&A?
it's in the Q&A. It's in the Q&A.
Simultaneously update call on main canister and cross canister call. It depends on what you mean by simultaneous. So nothing is going to happen. I think I see what you're saying. Let me know if this is what you're saying. So I think what you're saying is like um, some service dot update call and some service dot query call, right? Some other service. And you're saying, can you do this? Is that what you're asking?
Oh,
Because
we
that's
cannot see the screen right now.
sorry. If you're asking if you can do this, um, yeah, you can do that. I think. I don't see why. And you could await them like this, for example. In this case, it would do that one and wait and then do that one. Oh, but what you could do is you could just do like promise.all and then put these in here. You have to call these. And then it would fire both of them off basically simultaneously, not quite. And then you could just await that. Yeah, it would send this one off and send this one off. And then it would just wait for both of them to return. So I don't know if that's what you're asking, but if you do want to like message me or in the Discord or something, open a question and explain in more detail exactly what you mean, then I can hopefully help you get those semantics.
There is a follow-up question on the randomness. So it's more like on the protocol level, but essentially the question is the randomness the same in every node executing your randomness?
Yeah, the randomness is a protocol level API. I don't know what you mean by the same on every node. The nodes in the subnet uh, generate the randomness in a threshold manner. So it's a very secure, verifiable randomness that no one node would be able to generate itself. So they work together to generate the randomness. So it doesn't matter, like you will per update call, you'll get, I think, the same randomness every time you call that inside one update call. But it doesn't matter what node you're on. You're not. There's no concept of being on a node when you're doing an update call. Also, don't do randomness inside query functions. Um, yeah, you can't even get randomness from the. You can't call the raw ran thing from a query function. You have to call it from update function. And if you're doing like math.random or something in a query function, you'll notice that the randomness will not be saved. Like the under the hood state's not going to be saved, and so if you call math.random from a query function and then call it again, I believe that will return the exact same randomness every single time. So you need to do random stuff inside update functions, basically.
So there is a question, can you show an example of, um, sorry, I missed it. Uh, an example of deploying canister dynamically.
Deploying a canister
So
dynamically?
from within a canister, I don't know if there is such an example in Hazel.
Yeah, I can
Yeah,
just point to it.
from deploying canister from another canister, essentially.
Yeah, you do like this. This is an example of how you do that. So basically, you call the management canister, and then you call install code, and you put in the canister ID, and then you put in the WASM module. So you'll need to compile that WASM module separately and provide it in here. And then you provide any arguments to the init parameter, and then you give it enough cycles, and then you call it. So basically, to do this, you need to use the management canister to install code, create a canister. Yeah, create a canister. First, you would create a canister, and then you would install code into the canister. And you can uninstall, like, yeah, the management canister has all of that for you. So
So I'm dropping a link in the description, in the chat. It's a video about randomness from Manu, which is working at Definity and is on the consensus team. And so it explains everything you need to know about how randomness is managed. And it's yeah, it's at the protocol level, so it has nothing to do with Hazel essentially, but it's more something that requires cryptography and deep dive into how the IC works. It's very interesting though, if you want to watch. Yeah, I link the full video. What is the best practice for managing data? Should we store each each has a unique store and its method has a separate canister. I think the
There's
question
no,
is essentially single canister or multi-canister.
I don't know. There's no best practice. Depends, and it's a topic of debate. For me and for Dimension Labs, I want us to focus on the single canister experience with our GraphQL database because that will give you the best developer experience. Other people believe that they want to focus on embracing the cross canister experience. So there's just trade-offs. Like going cross canister is extremely complicated, and staying in a single canister is extremely not complicated. So if you don't have to go cross canister, then I would not do that. So for your project now, I would definitely keep it in a single canister. That'd be my recommendation. And then just think about how much you need to scale. Does a DAO really need more than 64 gigabytes of storage? I just highly doubt a DAO, for example, that's just one application, would need that much storage. Or a front end canister. A front end canister probably doesn't need that much storage either. So single canister is perfect for those situations. But what if you have, you know, a video, like a YouTube style thing? Well, then if you do want it to scale, like video is like the biggest amount of data. It's the video applications will probably be storing, you know, the most amount of data possible. Therefore, you would probably be required to go cross canister at that point. But I would recommend to just keep things as simple as possible to start and don't try to overcomplicate and scale when you don't need to.
Okay. Best lecture, someone said.
Sweet.
All right. So yeah, next lecture in 1 hour for the HTTP out calls. And I'll see you there, everyone. Thank you, Jordan.
You're welcome. I saw another question, by the way. Do we want to answer that?
The last one, what can't ISO do that Motoko can't? That, yeah, the other
I
one.
don't know. That might take a while to answer. So, uh, I'll give a short. I mean, it's like Azel can do things that maybe Motoko can't, and vice versa. So, but I think the general concept is Azel is very full featured with access to the IC APIs. But the main drawbacks would be it's less mature, so there could be bugs or security vulnerabilities, and it costs more. So that's the basic thing. But for example, Motoko doesn't have npm packages, right? And Motoko can't run arbitrary Rust plugins like Hazel can right now and stuff like that. So it just depends.
Yeah, we can maybe do like a deep dive next lecture if we have like maybe 20 minutes at the end where you can go in full details like comparing Azul, the benchmark you've been doing and all
Yeah.
that good things.
Okay.
All right. See you. See
Yep. See
you
ya.
all.